In this lesson, we are going to look at the relationship between pressure, volume, and temperature. These are going to be the gas laws. And we're not going to just look at how the variables are related. We're going to look at the formulas that are used to quantify those relationships. So let's get started. Let's think about the factors and the way the variables are related. What kind of things affect gas pressure? We studied the kinetic molecular theory already. You know that pressure comes from motion of particles and the collisions that they have inside their container. So the first variable I want you to think about is the amount of gas. If you put more gas in a container, it makes sense that the pressure is going to increase. You'd have more collisions. Think about blowing up a balloon and how it gets tighter and tighter the more air you put in there. The second variable is the size of the container, or the volume. If you change the volume of the container, you're going to change the pressure. Try to think about forcing a certain amount of air into a smaller space. It's going to be difficult to do. And finally, heating, you know, has an effect on gas pressure because we know that temperature changes the kinetic energy of the particles. The more energy the particles have, the more collisions they'll have, and that's going to change your pressure. So let's look at these variables along with pressure two at a time and come up with the equations to represent them. Now this first experiment is called Boyle's law. On the left slide you see that the volume of the container is 4 liters. That's the yellow box in the cartoon. The mass of the gas is indicated by the number of black dots. And below the yellow box, the pressure on that left side is 1 atmosphere. The temperature is 300 Kelvin. Now what we're going to do, as we go to the right side of the slide, you can see that they've added an extra green weight on top of that box, so the volume decreases to 3 liters. The mass of the gas stays the same number of black particles, and the temperature stays at 300 Kelvin. So what's changed is the pressure. As the volume went from 4 liters down to 3 liters, the pressure went from 1 atmosphere up to 1.33 atmospheres. That's the relationship. As volume goes down, pressure goes up. Let's take a look at that. We say from math that those are inversely related variables. If you look at this graph, on the x-axis is going to be the volume, and on the y-axis is going to be pressure. And you can see that as the volume goes down, or as volume gets smaller, pressure gets higher. They move in opposite directions. So the pressure and volume are inversely related. Remember, what we've kept constant here is temperature and amount of gas. Let's work a problem with Boyle's law. When you read a word problem, the first thing you need to do is figure out what all of these numbers represent. So we're looking at this weather balloon, and we know the conditions that it's launched from Clemens. We want to find out what the new volume of the balloon is at a new pressure after it goes up into the atmosphere. So I would suggest making a list, kind of like this. I've listed my first set of conditions, the volume and the pressure in Clemens, and I listed a second set of conditions, V2 and P2, for the conditions up in the atmosphere. Now this is going to be a Boyle's law problem because all I have are pressures and volumes. Now we're going to plug into the equation, and we want to solve for that second volume. You do it like this. You're going to take those givens and substitute into the formula for Boyle's law. So P1 is the 0.97 atmospheres, and V1 is 156 milliliters. P2 is 0.13 atmospheres, and V2 is my unknown. Now I can go ahead and do the math here because the pressure units match and they're going to cancel out, and the volume answer is going to be in milliliters, just like my first volume was given. So you do the math and rearrange. You want V2 by itself, and you get 1,164 milliliters. Now this answer makes sense because the pressure has gone from 0.97 atmospheres down to 0.13 atmospheres. As the pressure goes down, the volume goes up. So I know I should have gotten an answer larger than 156 milliliters. Got it? Let's look at another one. Now in this cartoon, we're looking at a different law, Charles' law. You can see here on the left side that the volume of the container is 4 liters with a certain amount of gas. The pressure is 1 atmosphere and the temperature is 300 Kelvin. Well, what happens on the right-hand side is that we lowered the temperature. The sample was cooled down to 225 Kelvin. See how the flame has disappeared? And the result is that the volume of the box, the yellow area, has gone down to 3 liters. So as the temperature goes down, the volume goes down too. This is the exact same thing that happens to the basketball that you leave outside in the wintertime. So let's take a look at this formula. In Charles' law, the relationship between volume and temperature is a direct relationship. And you see here on the graph, volume's going to be on the y-axis, temperature's going to be on the x-axis. As temperature goes up, volume goes up. As temperature goes down, volume goes down. The things that are constant here are the pressure and the amount of gas in the sample. I want to warn you to always use Kelvin temperatures when you work these problems and look at the relationships with temperature. If you work them in Celsius, you're going to get the answers wrong. So let's work a problem. Now you know our most famous graduate is Chris Paul. He left his basketball outside in the snow when it was 36 degrees, and the volume of the basketball was 124 centimeters cubed. We want to find out what's the new volume of the basketball if the temperature got down to 25 degrees Celsius that night. So again, let's make a list of what we know. I know the initial volume of the ball and I know the initial temperature, but I'm going to add 273 to turn that into kelvins. Likewise, I know the temperature dropped to 25 degrees Celsius, and I know that I need to add 273 to that to give me 298 Kelvin. Now let's find that second volume. This is going to be a Charles' law problem. The formula for Charles' law is going to be V1 over T1 equals V2 over T2. So we're going to take what we know and substitute in. Don't forget to use the kelvins. Now here's the plug-in. You've got to get V2 isolated, so use your algebra. You want to multiply both sides by 298. Now if you do that and you work your math correctly, I think you're going to get 120 centimeters cubed. Now think about that answer. Does it make sense? Well, I know that the temperature went down, and I know that volume's directly related. So if temperature goes down, volume should go down. So it does make sense that the volume went from 124 centimeters cubed to 120 centimeters cubed. Use these predictions to help you decide if you've worked your problems correctly. Alright, the third law I want to look at with you is Gay Lussac's law. What's constant here is the mass and the volume. We're going to look at temperature and pressure. It turns out that as temperature goes down, pressure goes down too. Think about the basketball in the winter. If the molecules are moving slower, you're not going to have as many collisions, so the amount of pressure inside the ball will decrease. I still want you to use those Kelvin temperatures, but when you look at Gay Lussac's formula, it's very similar to the Charles' law formula we just looked at. Here's the problem. We know that polar bears live at standard temperature and pressure. Remember, that's 0 degrees Celsius and 1 atmosphere of pressure. So let's figure out what's the pressure in space where the temperature's a lot colder, negative 178 degrees Celsius. Make a list of what you know. We know 0 degrees Celsius, but add 273 to get that Kelvin, and do the same thing with T2. We know that standard pressure is 1 atmosphere. Remember, we're looking for P2. So this is going to be a Gay Lussac's law problem. The mass and the volume here are constant. We're going to plug into the formula for Gay Lussac's law with our Kelvin temperatures and solve for that pressure. This is what it'll look like. Plug in. You want to solve for P2. So we need to use our algebra, multiply both sides by 95 Kelvin. And if you've done your math correctly, you're going to get 0.35 atmospheres. Now think about the predicted answer, and does this make sense? Temperature went from 273 Kelvin down to 95 Kelvin. If temperature goes down, what should happen to pressure? Well, it should go down. So from 1 atmosphere down to 0.35 atmospheres definitely makes sense. The pattern has been followed, and our prediction proved true. Now here is one combined gas law formula that has all three variables. You don't have to memorize Boyles and Charles and Gay-Lussac's laws. You can just learn the combined gas law formula and you have all three of those others. It's really easy. Think about Boyle's law. Remember how it was just P1V1 equals P2V2? If the temperature is not involved in the problem, you can just erase that variable, and what you're left with is the Boyle's law formula. It works the same way for Charles and Gay-Lussac's laws too. If a variable is not given in your problem, or if it remains constant, you can just erase it. Now we are going to do combined gas law problems where all of the variables are changing at the same time, and again you're going to be able to use this formula. The only thing that's harder about the combined gas law is that there are more numbers and you can't really predict what type of answer you're going to get because more than one variable is changing at a time. So I hope that helps. You're starting to see how those relationships can be quantified, and we'll work some more problems together next time in class.